You should behave with your databases and your application in general. So let's start with the first problem. Databases are really hard. And the reason they are hard is that they're both inscrutable. They are really complicated. They are you have so many different things that you have to get just right. At the same time, they're super critical for your system. Oh, I need to get something working. The data needs to come from the database. There's no other way of doing that. So how do I build my features? Why do I need to know about the physical structure of the data on disk in order to show you some data? That doesn't make any sense. That's really complex. So let's see if we can do better, or let's see how we can do better. And while I develop an application, I often feel like I'm on this side, this super complex, I have to fight to get everything done. Oh, I have to pull data from the database. I need to know how to make the query efficient, to make sure that I'm properly using caching, that I'm not overloading the system, that I'm properly loading the right data, not too much, not too little, etc. So many minutia, little details that I have to deal with. At the same time, I have so many other stuff that I have to do in order to get a good application. Oh, I need this layout to be responsive, and I need to be able to support the new iPhone, and there is a new flip phone going out, and I have to support whatever weirdness they're doing there, and things like that. And I really want to be at this level. Oh, I get the data, and then I can focus and add business value. Actually create something that means something, and not, oh, I managed to get the data out. One of the reasons that there are so many CRUD applications is that the process of getting and storing the data from a database is so complex. Now, I have to admit, I'm somewhat of a nerd. I'm speaking here, and my career certainly shows to that. And I find that databases are one of the purest expressions of computer science. If you go and look at the curriculum, what you learn, whatever this is, algorithm, analysis, all of that is relevant directly to databases. Oh, you learn about compilers, guess how you query databases. Oh, you're talking about optimizations, mostly apply to databases, cheat compilation, whatever. Basically, any interesting topic in computer science, whatever from distributed systems to concurrency, has probably been explored in the context of databases, which means if you build databases for a living, you're in a really great shape because you have this huge, amazing body of knowledge that you can use to build all sorts of interesting things. I love it. I think it's amazing as a database developer, as someone who is an application developer who just want to write my application to get things done. That's really bad place to be at. So I used to be a database performance consultant. I would go to companies and I would tell them, hey, I know that you're doing things wrong. And here is how and here is why. And that was an incredibly frustrating experience because I would keep seeing really smart people fall down to the same problems time and time again. And like, they're not stupid, they're not evil. What make it? What's the reason why we got to the point where they keep falling into the same trap? Or you have a single page that require 500 database queries. That's like Obviously bad idea. But he did that. And then they called me and, oh, please fix that. And I had to meditate just to be able to answer properly. This was pretty much me at the start of every engagement. And I think that a large part of that comes from the way that people design databases. So someone comes with an amazing idea for how to persist data to disk. Whatever this is, a log structure merge for hard disk, or there's now new technologies, faster for Microsoft for NVMe and a bunch of other stuff. And I'm sorry that I'm using, acronyms that you may not be familiar with. But the basic idea is that, oh, I have a way of dealing with something that would make a great database. Let me go ahead and build that, and this would change the world. And the only problem with that is that you take all of the complexity and throw it into a pot. And the only thing that you get out of that is more complexity. It's interesting because when you think about what is required from a database, usually make it go fast across everything else. Make it go fast. That's the only metric that you measure on, because it makes for good benchmarks, because the super interesting scenarios are where you're really under load and scaling or whatever. But I think that this misses a really critical aspect. If I can go really fast, but I need a team of experts to hold my hands at every single point in time, that's not really a good idea. A Formula One car is an amazing piece of engineering, but it is also making tons of assumptions. Where is it running? How is it running? Who is maintaining that? You're going to take the car to the shop multiple times during a race versus, I need my daily driver and I want to hit the garage once a year. And if you can push that to once every 2 or 3 years, that's amazing. So when we think about databases, when we rethink about how we want to think about databases, let's see where we want to be. As an application developer, I want the database to go away. I need it to work, but I don't want it to be anywhere in my list of things to do. So let's look. I started building RavenDB about 15 years ago because I was sick of having to deal with annoying databases. I was frustrated and angry about, oh, I have to deal with another customer who is coming to me and I can just regurgitate, just give them the same answer over and over. I mean, it was very nice from a financial perspective, but I really wanted to build and work on something good. So the design process for RavenDB actually started drastically different from how most databases are built. To start with, I had no idea what I was doing at the time. But this is fun because I also was very focused on where I wanted to go. So I want a system that would match what I need as an application developer. And it should be smart and should do this and that. But the whole point is that I should be able to build a system in peace, and the database should manage itself and not make me worry about it. That's the point. I want to be free to build my system and not worry about persistence. And that turned out to be quite a challenge. And the reason this is a challenge is that databases are not complex because database developers are evil. The problem space is super complex. The problem space is something that you have to deal with. And as you try to solve the challenges in order to build a good database, then things become complex. unless you set out to uncomplex them as a core feature. So to give you two examples of things that make things a lot more complicated. As a database, I'm storing data to disk. So if I tell the disk, here is some data, store it, and it tells me, okay, I will do that. And then I realize that it lied to my face, that is a problem. And my ability to tell my customer, hey, your disk is a liar is limited. So you have to deal with a whole bunch of physical components who sometimes fail, sometimes they literally lie to you. Sometimes there was a huge mess called fsyncgate a few years back. And it turns out that Postgres, which is an amazing database, has huge community, huge amount of a huge amount of trust and practical experience. They read the documentation wrong. And for the duration of Postgres, a particular error condition will cause data corruption. If you really care about it, go read about fsyncgate. That was a huge mess at the time at the database community. And so, and the underlying reason is that this could lie. And the operating system would lie to you about it, and everything would lie to you about it. And you have to be super careful when you write data to disk and verify how you do it. And it's a whole thing. The other stuff is that, oh, you're building a database, then you have to understand that everything around you is a hostile entity that is going to attempt to steal your data, corrupt, whatever. So those are just two of the most critical examples that I could think of that would demonstrate what is the problem space that we have to deal with. The other side is that I have to deal with, well, you want to build your applications, but you want to change the data, you want to uh, 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 give your user the ability to run any query that they want, and you want to do that without paying any attention whatsoever to the database. And to large extent, what you're seeing here, you want to go on the field of flowers and not realize that you're actually crossing this scary chasm of demonic level of complexity. And now that I set out to scare a little bit about how databases are complex, let's see some actual code. And this is really interesting because I was able to squeeze quite a lot of stuff into a single slide. And in here, you can see my model. And I use the invoice model, which is as simple as possible. But I wanted to look into this for a second. And I'm using TypeScript as the programming language and try to imagine building the backend for this. What it would take to persist an invoice to a database. How many tables are you going to have? I'm going to make it even more fun for you. Payments, you need to support wire transfer and credit cards and PayPal. And every time that I raise another finger, I can hear people squeak in pain because of the impact of the complexity. And there is the complexity of, oh, how do I integrate with PayPal? And there is the complexity of how do I persist radically different data? Oh, I need to store wire transfer and the token from the credit card company in some manner. And how many tables and how do I modify the data and how do I later generate a report on that? So that's one side of things. And the way that I love to think about it is that I think that there shouldn't be this huge divergence, this impedance mismatch between the way you store data in your database and the way that you store data in your system, in your application. So here is one way of doing that. You can see here is an invoice. And this is a relatively simple one, but you can see what we have here. This is a really simple JSON document. And there is a one-to-one match here between the JSON document that I have in the database and my model. This is a big divergence from how you typically model in a relational database. But it has a huge number of benefits in simplicity, ability to evolve your model, ability to actually have a serious conversation with your business. Oh, here is your documents, your forms that you're dealing with, and there is a one-to-one match to what we are storing in the database. Another aspect here, look at how we have here, we have logic that we can apply. And if you look at this code right now, you can see that I'm making a query, and the query is pretty obvious what's going on. And then I can create an invoice if I don't have one, and then I apply some logic. So I have a very rich model to work with. And this rich model is translated into one-to-one almost to how it persists to disk, persists to the database, then to disk. But the whole point of doing it in this manner is that this frees me from the whole impedance mismatch. This is a radical change in thinking, but it has tremendous benefit for you. But you know what? This is not specifically for a database engine. This is how you store the data. So let's see some other things about using the database. And you can see here something really interesting. This particular query is being translated to this thing that is sent to the database engine. And now we have something really interesting. I load data from the database, I modify it, then I call save changes. This is called unit of work or change tracking. And the whole idea is that I can modify my application, my model in my application, and not have to track persistent concerns. Or I have to remember to register the new invoice item. No, you don't. Add it to the invoice and call save changes. Then you're done. And now I want to look into this. I'm just here sitting down, writing the code. I know that I have the phone number. I have to register the new charge for this SMS. I'm writing this code. Am I done? Well, this is obviously demo code. There's so much other stuff that I have to deal with. For example, what happens if I have a lot of invoices? This query that I have here is going to have to run through all of them. So I have to figure out how to make the database make it go fast. Let's go back here and let's look at this query. And I'm going to run this query and it's going to find me some results. And you can see that it found it in some time. By the way, notice that I'm using the public live instance of RavenDB. Next time that I'm going to issue the query, it's going to be much faster. Why is that? Take a look here. What we have here is an automatic index. It was created by the database engine itself. Why? Because I issued the query. Let's delete this index. Now I have no indexes whatsoever. Let's run the query again. And again, it takes a while because we have to create the index. Here's the index back again. And this may seem like a small feature. Because again, you're seeing I'm running a query, I have an index, moving on with my life. This actually has a huge impact on the way that you operate. Because as a developer, I'm sitting there writing code and focusing, okay, what is the query that I want to run? and then I run the query. And then it is the responsibility of the database engine to make it go fast. It's not my responsibility as the application developer. You see this happy kid over here? He's happy because he's running queries and there is a whole team maintaining the garden. That's the same thing that you ought to have. That's what we implemented in RavenDB specifically for that scenario. That has a lot of impact on tomorrow as well. Because, oh, there is something that you need to change. Well, you go ahead and change that. And you change the query. And the database will adjust. Speaking of performance, we also need to deal with caching, right? I mean, this is a pretty simple query, but what happened if it was a more complex one? Well, there is caching involved here. You're not seeing the code because it's not there. But the whole point, if you issue this query twice, including across different sessions, then something really interesting will happen. When the server answers you, here is the result of this query. And I can actually show you to you. Let's go here. And here is the result. And you can see this guy over here. Here is the result of the query. And then I have this guy, result etag. This is a number that is being produced by the server. And the next time I'm going to issue this query, I can provide it with the right result etag, which happen automatically when you use the client API. And the server doesn't need to run the query. Instead, there is an optimized code path to check whatever the result of this query have changed. So now we have caching. In fact, we have more than caching because we have caching that check with the server if everything is okay. And then we save on network bandwidth and we send on processing time and we saved on parsing time on both server and client. And the key aspect here, oh, you don't need to generate appropriate middleware or something like that. It's just there. You expected to write the simplest possible code. And you're expecting that it will do the right thing. In the same sense, what happens if I'm running in a cluster and one of the nodes is down? Where is the code to handle that? According to the way I'm thinking about this is not your responsibility, this is mine. So the code that you see right here in front of you would probably handle a failed server completely transparently to what you're doing. In the same sense, I now need to change the rules. There is a new model changes that I need to do. I don't need to open Pandora box in order to do that. I can just build a system, make the changes, and the database will adjust. Now, to be clear, I'm speaking at roughly 10,000 foot level. And the way that I'm speaking about this is I'm trying to give you the gestalt, the way that I'm thinking about this. There are literally dozens of features like that. Here's another example. And you can see that right now I want to show some details for the user. And I need to show the data about the invoice and also about the relevant contract. So I'm doing this. I'm telling the database, hey, when you give me the results for this query, I want you to include the details from this path. And now this portion is not a remote call. I was already provided with this relevant information when I ran the first query. Here's another example. I want to show you a grid of results. So show me the first 5. In order to show you the grid of results, I need to figure out how many results there are. And in most databases, you need to make 2 queries. One to get the first 5 results, and the next to get the total number of results. And that's kind of stupid. Why would I want to do that? And here you can see that in one shot to the database, I'm getting both pieces of data. And if you look at the entire slide, everything is done. And again, those are small features, but that means that instead of hitting the database 4 times, 5 times, however many specific contracts we have, we hit it once. That has a huge impact on your performance. Beyond that, a core design principle is that I'm not assuming that you have an expert DBA on hand. So the database engine is meant to handle with everything. Whatever this is a new query, or I need to figure out what to do with a burst of additional load on the system, all of that. So the whole idea is that I want to have a grown-up database. And I have a really good example of how this came into being. RavenDB, the engine, goes to tremendous lengths in order to figure out what is wrong. And if it can't fix it, it will tell you what's going on. So you can see here, this is an alert that you get from RavenDB if your disk is slow. And the reason we have this is that we had a production issue with a customer. Sometimes the system is slow, and we couldn't figure out why. They were running on fast disks, on fast SAN, and no resource starvation or whatever, just sometimes slow. It took us 3 months to finally gather enough information to be able to say, oh, there is a problem with the disk. The disk is sometimes slow. And it turned out that they were running on the SAN, and the quality of service settings weren't set up properly, so we're getting maybe 1% of the actual processing power that we had. And one of the things that we did out of that is go ahead and implemented the monitoring for that. So next time I can tell you, hey, for this particular file at this particular time, this is what we're seeing. Go talk to your storage team. Or if you're running on the cloud, go buy a better disk. So you don't have to guess. You don't have to go into this fog of war to understand what's going on. And we kept doing that for 15 years. So at this point, we're pretty good at either fixing things if we can do that, or being able to tell you exactly what the problem is. To summarize, I don't know if it comes to the screen, but I really love databases and I think they're fascinating. And I've been working on them for more than 20 years. I'm going to assume, and the way that I approach things is that I love databases. You want your system to work. You want using the database to be like driving on the highway. It's a key infrastructure, but you never want to say, oh, listen to the story about what happened today on my way to work. It's always a bad thing. And I want you to literally forget that there is a database in the backend. Because if the database is completely transparent to you, then we did our job right. Thank you very much. We have a booth at the TDC and we would love to see you there. And if you have any questions, I will be very happy to take them. And if not, feel free to send me an email to this address, oren@ravendb.net. I'll be very happy to answer any questions that you have. Okay. Thank you, everyone. Goodbye.